Maintenance secrets of the railway industry. Railway ballast requires sophisticated maintenance procedures that most travelers never see but are essential for safe train operation. These maintenance activities occur during scheduled track closures, often at night when passenger services stop running. Maintenance crews work under strict safety protocols because they operate heavy machinery near active railway corridors. The maintenance window typically lasts only 4 to 6 hours, requiring crews to complete complex operations efficiently. Track supervisors coordinate these activities to minimize disruption to train schedules while ensuring all safety requirements are met. Emergency maintenance procedures also exist for situations where ballast problems develop unexpectedly and require immediate attention to prevent service interruptions or safety hazards. Ballast cleaning operations use massive machines called ballast cleaners that excavate, screen, wash, and replace contaminated stones while trains continue operating on adjacent tracks. These machines weigh over 200 tons and operate on railway tracks using specialized bogies designed for heavy equipment. The cleaning process begins with excavation systems that dig beneath the sleepers to remove contaminated ballast down to the subgrade level. Conveyor systems transport the excavated material to screening equipment that separates reusable stones from fine contamination. Washing systems use high-pressure water jets to remove clay particles and other debris clinging to stone surfaces. Clean stones return to the tractive distribution systems that place them precisely around the sleepers. The excavation process requires precise control to avoid damaging underground utilities and drainage systems. Operators use depth sensors and GPS guidance to ensure consistent excavation depths across the work area. The screening equipment includes multiple mesh sizes that separate stones into different categories based on their condition and contamination levels. Heavily contaminated stones go to waste disposal systems, while partially contaminated stones receive additional washing. The washing process uses recycled water systems that filter and reuse cleaning water to minimize environmental impact. Distribution systems include compaction equipment that ensures proper stone placement and density around the sleepers. The life cycle of ballast stones typically spans 15 to 30 years, depending on traffic density, climate conditions, and the quality of the original material. High-traffic freight corridors experience faster ballast degradation because heavy axle loads create more stone breakage and contamination. Passenger railways with lighter trains but higher frequencies still cause gradual ballast wear through repeated loading cycles. Climate factors affect ballast longevity through freeze-thaw cycles, chemical weathering, and moisture-related degradation. Premium ballast materials like granite and quartzite last longer than softer limestone or sandstone alternatives. Regular maintenance can extend ballast life by removing contamination before it reaches critical levels that require complete replacement. Contamination occurs gradually as ballast stones break down under repeated loading, creating fine particles that fill void spaces and reduce drainage capacity. This breakdown process accelerates when trains apply dynamic loads during acceleration, braking, and cornering. Stone-on-stone contact during train passage creates abrasion that generates fine particles over time. External contamination sources include wind-blown soil, vegetation growth, and spillage from cargo trains. Coal dust from unit trains creates particularly problematic contamination because it forms cohesive mixtures with water that severely reduce drainage. The contamination accumulation follows predictable patterns that maintenance engineers monitor to schedule cleaning operations. Modern maintenance strategies use ground-penetrating radar and other technologies to assess ballast condition beneath the surface without excavation. Ground-penetrating radar systems emit electromagnetic pulses that penetrate the ballast layer and reflect off interfaces between clean ballast, contaminated areas, and the subgrade soil. Signal analysis software interprets these reflections to create detailed maps showing contamination distribution throughout the ballast depth. This technology allows maintenance crews to identify problem areas before they affect train operations and helps railroads reduce costs substantially because they avoid spending resources on areas that don't require remediation. Ballast shoulder maintenance involves reshaping and compacting the stone slopes alongside tracks to maintain proper drainage and prevent lateral track movement. Shoulder maintenance equipment uses adjustable mold boards to reshape ballast slopes to specify profiles. Compaction systems ensure adequate stone density in shoulder areas that provide lateral track support. Proper shoulder geometry directs water away from the track center line toward drainage ditches and collection systems. Inadequate shoulder maintenance allows water to pond near the rails, accelerating corrosion and creating safety hazards. Specialized tamping machines compact and align ballast stones around sleepers, using synchronized vibrating tools that optimize stone positioning. Tamping machines use hydraulic systems to insert vibrating tools beneath each sleeper simultaneously. The vibrating action rearranges ballast stones into optimal positions that provide maximum support and load distribution. Computerized control systems ensure consistent tamping pressure and vibration patterns across all sleeper positions. Modern tamping machines include laser guidance systems that maintain precise track geometry during the compaction process. Predictive maintenance programs analyze ballast degradation patterns to schedule cleaning and replacement operations before safety issues develop. These programs use databases containing historical maintenance records, traffic loadings, and environmental conditions for each track section. Statistical analysis identifies correlations between operating conditions and ballast degradation rates. Machine learning algorithms process this data to predict when specific sections will require maintenance attention. The predictive models consider factors like train speeds, axle loads, weather patterns, and previous maintenance history. The economics of ballast maintenance involve balancing the cost of cleaning versus complete replacement, with decisions based on contamination levels and remaining stone life. Transportation costs often exceed material costs for ballast, making quarry location relative to railway projects a critical economic consideration. Research from Ballast and Foundation Materials programs shows that transport and purchase price dominate ballast cost decisions. Quality versus cost trade-offs require engineers to balance initial ballast expenses against long-term maintenance costs and service life expectations. These maintenance secrets reveal why railway systems can operate safely for decades while handling millions of tons of cargo and passengers annually. The sophisticated maintenance procedures represent accumulated knowledge from over 150 years of railway engineering experience. Modern technology enhances traditional maintenance methods while reducing costs and improving safety outcomes. Yet as these massive maintenance operations continue worldwide, the industry faces growing pressure to address the broader implications of ballast production. Quarrying operations for ballast production significantly impact local ecosystems, requiring careful environmental management and restoration planning throughout the extraction process. Large-scale quarries remove entire hillsides and disturb underground water systems that support surrounding vegetation and wildlife communities. The extraction process strips away topsoil that developed over centuries, eliminating habitat for countless organisms that depend on these established ecosystems. Blasting operations fragment remaining habitat areas and create noise pollution that disrupts wildlife behavior patterns and migration routes. Dust from crushing operations settles on nearby vegetation, reducing photosynthesis efficiency and harming plant communities that form the foundation of local food webs. Heavy machinery compacts soil around quarry sites, preventing natural regeneration of native species and creating long-term ecological damage. Water runoff from quarries carries sediment and chemical residues into nearby streams and rivers, affecting aquatic ecosystems downstream. Environmental management at quarry sites now includes detailed impact assessments before operations begin to identify and protect sensitive ecological areas. These assessments identify endangered species and critical habitats that require protection during extraction activities, ensuring compliance with environmental regulations. Quarry operators develop comprehensive restoration plans that specify how sites will be rehabilitated after stone extraction ends, often creating new ecological opportunities. Progressive restoration allows portions of quarries to be rehabilitated while other areas remain active, minimizing the total disturbed area at any given time. Native seed banks are preserved and used to restore indigenous plant communities that support local wildlife populations. Artificial wetlands treat quarry runoff before it enters natural water systems, removing contaminants and sediments. Wildlife corridors connect fragmented habitats around quarry boundaries, allowing animals to move safely between remaining natural areas. Transportation of ballast materials often involves long-distance trucking or shipping, contributing to carbon emissions that railways are working to reduce through improved logistics and route optimization. Many railway projects cannot source suitable ballast locally, requiring transportation across hundreds or thousands of kilometers to reach construction sites. Premium granite from Scandinavian quarries travels to construction sites throughout Europe and beyond, while Australian quartzite ships to North American mining railways for heavy haul applications. These transportation networks generate substantial carbon emissions that offset some environmental benefits of rail transport compared to other freight modes. A single ballast shipment can involve 50 to 100 truckloads, each consuming diesel fuel and producing exhaust emissions during transport. International shipping of ballast uses heavy cargo vessels that burn marine fuel oil with high sulfur content, contributing to air pollution and greenhouse gas emissions. Railways are implementing transportation optimization strategies to reduce these emissions while maintaining access to quality materials. Regional sourcing policies prioritize local materials even when they require more frequent replacement, reducing transportation distances and associated emissions. Improved logistics coordinate ballast deliveries to minimize empty return trips and optimize vehicle utilization rates. Multimodal transportation combines rail and truck transport to reduce road miles and take advantage of rail's superior fuel efficiency. Some railways invest directly in quarries near major maintenance facilities to minimize long-distance transportation requirements. Electric vehicles are beginning to replace diesel trucks for short-distance ballast transportation in urban areas. Rail transport of ballast from quarries to construction sites reduces carbon emissions compared to exclusive truck transport over long distances. Recycling programs now recover and process used ballast, removing contamination and returning clean stones to service rather than disposing of them in landfills. Traditional ballast disposal involved hauling contaminated material to waste sites. Modern recycling programs use mobile processing equipment that travels to work sites and cleans ballast on location, reducing transportation costs and environmental impact. The cleaning process separates reusable stones from fine contamination through screening and washing operations that restore original specifications. Recovered stones undergo quality testing to verify they meet original specifications for strength and durability before returning to service. Recycling typically recovers 70% to 85% of original ballast volume while reducing new material requirements by the same percentage, significantly reducing quarrying demands. Advanced recycling technologies continue improving recovery rates and stone quality through specialized processing techniques. Density separation removes lightweight contaminants like vegetation and plastic debris that accumulate during service. Magnetic separation extracts metal fragments from ballast contaminated by rail wear and maintenance activities. Chemical washing removes oil and grease contamination from ballast in industrial areas where cargo spillage occurs. Thermal treatment can remove organic contamination that resists conventional washing methods. The recycled ballast often performs as well as new material while costing 30% to 50% less than virgin stone, creating economic incentives for sustainable practices. Research into alternative materials focuses on using industrial byproducts like steel slag and recycled concrete as ballast substitutes to reduce quarrying demands. Steel slag from metal production has similar hardness and angularity characteristics to natural stone after proper processing. Processing removes harmful chemicals and adjusts particle size distribution to match ballast specifications for railway applications. Recycled concrete from demolished buildings provides another ballast alternative after crushing to appropriate sizes and cleaning to remove reinforcing steel and other contaminants. Geogrid reinforcement systems are being tested to enhance ballast performance and extend service life. Polymer-coated stones undergo durability testing to determine whether surface treatments can improve resistance to wear and contamination. Life cycle assessments compare the environmental impact of different ballast materials and maintenance strategies to identify the most sustainable options for specific applications. These assessments quantify energy consumption, carbon emissions, water usage, and waste generation throughout the entire ballast life cycle from extraction to disposal. Natural stone quarrying typically has high initial environmental impact, but provides long service life that amortizes the impact over decades. Recycled materials have lower initial impact, but may require replacement more frequently, affecting total life cycle impact. Transportation represents a significant portion of total environmental impact for most ballast options, making local sourcing increasingly important. Maintenance strategies affect life cycle impact through cleaning frequency and replacement intervals that determine total resource consumption. Water management at quarry sites addresses concerns about groundwater impact and sediment control during ballast washing operations. Quarry dewatering can lower groundwater levels in surrounding areas, affecting wells and natural springs that communities depend on. Sediment from washing operations can clog streams and harm aquatic ecosystems if not properly controlled through engineering measures. Modern quarries use closed-loop water systems that recycle washing water and prevent contaminated discharge into natural water bodies. Settling ponds allow suspended sediment to precipitate before water returns to natural systems, protecting downstream water quality. Groundwater monitoring ensures that quarry operations do not adversely affect local water resources that support both human communities and natural ecosystems. Biodiversity conservation efforts work to minimize quarrying impact on wildlife habitats and restore quarried areas for ecological use after extraction ends. These sustainability initiatives demonstrate how the railway industry is evolving to balance infrastructure needs with environmental responsibility through comprehensive planning. The development of innovative ballast materials, including recycled plastic composites and other sustainable alternatives, continues advancing as environmental pressures increase and traditional resources become less accessible. These environmental considerations increasingly influence the complex economic calculations that drive ballast selection and procurement decisions worldwide.